Here we're going to look at some one-dimensional solutions to Schrodinger's equation. In one dimension, we'll look at one dimension in Cartesian coordinates. So for applications in one dimension, psi of r and t becomes psi of x and t. So little psi of x times phi of t. In our Schrodinger's equation, our time-independent Schrodinger's equation in one dimension becomes negative h bar squared over 2m, second partial of psi with respect to x. Actually, this could be a full derivative, d squared psi dx squared, plus v of x minus e times psi of x equals 0. Here we see also that our potential energy function, v, is a function only of x. Now, what will distinguish the different applications, the different situations for solving Schrodinger's equation will be the potential energy function. What potential energy does the particle see? What does it experience? And everything else will be the same. The boundary conditions will be the same. Normalization, that requirement will be the same. The thing that will be different will be the potential energy function. Our first application is what's been called the free particle, or as our book calls it, the electron in free space. This analysis and solution will work for particles other than electrons, but we'll typically apply it to electrons. The thing to note is that it is free. The particle is free, it's in free space. There is no boundary or barrier that is hindering the position or limiting the position of the electron in any way. So the potential energy function, we're going to think about potential energy rather than say force, the potential energy function is 0. The particle sees or experiences a 0 potential energy, and it is therefore free. All right, so if we plug that into Schrodinger's equation, we obviously have negative h bar squared over 2m, partial of psi with respect to x squared, minus e psi of x equals 0. We can multiply times -1, do a little bit of algebra, and we get the second partial of psi with respect to x squared is equal to negative 2me over h bar squared psi of x. This is our differential equation to solve. E, we know, is going to be positive, it represents the energy. So this term here, 2me over h bar squared, is positive. We've got a negative sign here. All right, so let's solve that. This equation has the form d squared f dx squared equal to negative k squared f, where k squared is positive, we've got a negative k squared. If we guess that f is an exponential, then it turns out there are two solutions, and we find that the general solution to this second order differential equation is a constant here times e to the jkf x, e to the a times e to the jkx plus another constant times e to the negative jkx. And the a and b would be determined from the boundary conditions. Well, here we have k squared is equal to 2me over h bar squared. So k is the square root of 2me over h bar. And then psi of x is a, we have e to the j 2me square root over h bar x plus b e, or the exponential function, negative j 2me over h bar x. Now, we could have solved this in terms of sine and cosine, but complex exponentials are more conventional and actually simpler. Now, this is psi of x. We also know phi of x. So if we know that our capital psi of x and t is psi of x times phi of t, and with that, and we know what phi of t is. We've solved the time for the time dependence. So let's put all this together, multiply it together, and we can get our solution. The form of the solution. Our wave function for our free particle is a e to the, here's our exponent, j over h bar. There's a little bit of manipulation here, a little bit of algebra. Square root of 2mex minus e times t plus b e to the negative j over h bar 2me x plus e times t. Now, what we see, if you think back to what we learned about in electromagnetics, and looked at traveling waves, this looks like the traveling wave in the phasor domain. We could express this in terms of sinusoids, so we have cosine and sine terms, and we see traveling waves, real part, but the traveling waves that have a real part and an imaginary part. But both parts are traveling in the same way. Here we see the sign on the spatial coordinate being different from the sign on the time coordinate, time variable. So this is going to be a positive x traveling wave. And here we have that they have the same sign. So this is going to represents a negative x traveling wave. So the particle, the electron, or whatever the particle is, when it is a free particle, its wave function is a traveling wave. This is extremely important. Now, we also have, we go back to our notation here and say, let k, in terms of k being square root of 2me over h bar, and omega, the angular frequency of the particle, e over h bar, then obviously our wave function, we have a e to the j, we have kx minus omega t plus b e to the negative j kx plus omega t. And this looks very much like what we saw last semester in electromagnetics for traveling waves. K is our, well, in electromagnetics we call this our propagation constant, which we also said we could call it the wave number, which is now the term that we'll use here. So K is our wave number. And we can talk about phase velocity. Our phase velocity V sub p is omega over k. Recall this from our work in electromagnetics. Now this is a sinusoidal traveling wave, right? Just like we saw last semester in electromagnetics, it's sinusoidal traveling waves. the free particle is a sinusoidal traveling wave. Let that sink in. The free particle is a sinusoidal traveling wave. It's got a frequency, it's got a wavelength, it's got a wave number, which is the propagation constant, and we can also talk then about the wavelength. Well, let's think about that then. Got some really important conclusions from this for us. Our wavelength, lambda, is 2 pi over our wave number k, as we know from last semester with electromagnetics, with sinusoidal traveling waves. And so we plug in what we know k to be, and we have our wavelength is equal to 2 pi times h bar over the square root of 2me. So h bar is h over 2 pi, so this is h over the square root of 2me. Now, with de Broglie, from de Broglie, he said that the wavelength of a particle is h over p. And if we relate these two, we see that the momentum corresponds to the square root of 2me. But this gives us our old relationship between momentum and energy, kinetic energy. E is p squared over 2m. Wow. So the energy of the kinetic energy of the free particle is related to its momentum in the normal way, and then that's related to its wavelength in the same way that de Broglie postulated. But we also have that the momentum, square root of 2me, is equal to h bar k. So the wave number is proportional to the momentum. The wave number is proportional to the momentum. The momentum is proportional to the wave number through h bar. That would be the proportionality constant. All right, so we have this nice relationship showing up again. We have this important relationship. And if we go back and look at the wave number and energy, then we have k is equal to the square root of 2me over h bar, and now we know that k is the wave number, the propagation constant, which is related to the momentum. And in terms of k, wave number, the energy of a free particle is h bar squared k squared over 2m. And this is going to be an important relationship for us. In fact, looking ahead, what we'll see is that electrons and holes in a semiconductor, those that are free to conduct current, they'll have a wave number and they'll act like free. We'll actually be able to treat them as a free particle, but with a funny mass. We'll actually talk about that. But so this relationship is going to be really important, even though we don't have literally a free particle electron that's floating around in free space with no boundaries. We'll have something that looks a lot, that behaves like that in some ways. All right, so the free particle, or electron in free space.